Young's modulus, uniform bending, optic lever method. Now we want to determine the Young's modulus of the material of a given bar. So this is the experimental bar, it is given. We want to find the elevation first. Elevation means when it is loaded, the center is got elevated. That elevation is measured with the help of an optic lever. Now we are provided with an optic lever. This is an optic lever. Now this optic lever consists of a horizontal metallic platform with the 3 pins. The 3 pins forms the 3 corners of an isosceles triangle, and on the horizontal metallic platform vertically a mirror is fixed. Now this mirror is there. So that is the optic lever. Now when this optic lever is placed on a paper, and if we trace the 3 legs, now we can place on a paper, and the 3 legs can be placed, and the 3 points can be marked as ABC. We can mark the 3 corners. The 3 corners are marked as ABC, and then if we join this ABC, we are getting an isosceles triangle like this. Then the perpendicular from A, the single leg, to the base, that gives the A, the length of the optic lever, the length of the optic lever. Now we are provided with the experimental bar. Now to place the optic lever, the single leg is usually placed, or the single leg is placed on the experimental bar, and the other 2 legs are placed on a platform or a supporting bar. Here we are using a supporting bar, and that supporting bar is placed just behind the experimental bar, and then the optic lever is placed on the experimental bar. Exactly, the single leg is at the middle. So here the middle is 50. The middle is at 50. So it is placed. The single leg is placed on the reading 50 here. 50 here. Now the bar is loaded using 2 weight hangers. Say weight hanger 1 is here and the other one is here. Now the distance between the 2 knife edges, that is called the length of the bar, and the length of the bar is L. Here L is 40 centimeter, and the weight hangers are suspended at a distance of say P, and that distance P here is 10 centimeter. Now to measure the elevation produced when it is loaded, we are using a scale and telescope arrangement. This is a scale and telescope arrangement. A telescope is there, and that telescope is focused over the mirror. Then the mirror is placed such that the image of the scale is formed on the mirror. So we can move the scale and telescope arrangement such that the image of the scale is on the mirror, and we are looking through the telescope on the mirror. We are observing the scale. Using that scale and telescope arrangement, which is placed at a distance of say capital D. Now here capital D is about say 95 centimeter. The distance from the mirror to the scale, that is 95 centimeter. That is capital D. So these are the parameters that we used for the particular experiment. Young's modulus, uniform bending, the optic lever method. Here our aim is to determine the Young's modulus of the material of a given bar, subjecting it to uniform bending and measuring the elevation using a optic lever. So we have already seen what is the optic lever. So we are provided with the optic lever and the given bar and the knife edges. Then coming to the theory, the formula for the Young's modulus when it is in the uniform bending, y is given by the formula mgp L square divided by 8IE. mgp L square divided by 8IE, where m is, now here we can see the arrangement. The given bar is supported over 2 knife edges, and we are suspending 2 mass at the other at the 2 ends or at some position. The suspended mass is m, and p means that is the distance of the point of suspension from the knife edge, that is p, and L is the distance between the 2 knife edge. The distance between the 2 knife edge, that is L. So mgp L square, and 8I is the moment of inertia of the given bar, and for a rectangular bar I is equal to BD cube by 12, and for a cylindrical bar that is pi r raised to 4 by 4. And E is the elevation produced at the center of the bar, and that elevation is actually we measured with the help of the a scale and telescope arrangement and the optic lever. And when we substitute for a rectangular bar, I is equal to BD cube by, actually it is BD cube divided by 12, then what happens that this I is equal to BD cube divided by 12, then 8 and 12 cancels, then we obtain the formula 3 mgp divided by 2 BD cube into L square by E. Now this E can be determined with the formula E is equal to SA by 2D. So that is the formula that we used, where A is the effective length of the optic lever that we can trace and find out, and S is the shift that produced on the scale and telescope arrangement on the scale, and that we are taking in our experiment. So the experimental part is actually to determine the value of E using the formula SA by 2D. So S we are determining, the shift we are determining for a particular mass, and D is the distance of the optic lever from the scale and telescope arrangement. So using this formula we are calculating the value of E, and that value of E is substituted in this particular formula 2, and then the Young's modulus is determined. So that is the aim of the experiment. And coming to the tabular column, first we determine the breadth of the bar using a vernier caliper, then the thickness of the bar is determined with the help of a screw gauge, and to obtain the the optic lever is placed over a paper, then the 3 legs gives the traces A, B and C, A, B, C. Actually it is the 3 corners of an isosceles triangle. Then draw the perpendicular from C to the line AB, and that distance is A, and that is known as the effective length of the optic lever, Then the bar is supported on the 2 knife edges as we mentioned earlier. Say L is equal to 40 centimeter. Then the optic lever is placed with the single leg on the experimental bar and the other 2 legs on a supporting bar or a platform. Here in the diagram a platform is shown. Usually we are using a supporting bar. The 2 legs are on the supporting bar and the single leg is on the experimental bar. Now when it is loaded, what happens that the beam bends and there is an elevation is there. The mirror turns and then the telescope reading also change. The scale and telescope reading is changed. So the scale and telescope is arranged at a distance of D from the mirror of the optic lever. So that is arrangement. Now coming to the tabular column, we can see. Now this is the tabular column that we use. Initially we are suspending a mass W0. Then the telescope reading we have to take. There are 2 steps are there, loading and unloading. While loading we are taking the reading, so correspond to W0. Then another load is suspended, that is W0 plus M. Then W0 plus 2M, say M is equal to 50 gram or 100 gram. Each time we are adding 50 gram. Then W0 plus 3M, W0 plus 4M, 5M, 6M and 7M. Then each case we are taking the reading of the telescope reading, that is loading reading. Then the loads are removed one by one. Then we are getting reading corresponds to W0 plus 6M, W0 plus 5M, W0 plus 4M, 3M, 2M, W0 plus M and W0. And that is unloading. Now these 2 readings are almost same. We can take the mean of these 2 readings and that is marked as X0 for W0 load. X1 is the mean reading for W0 plus M. X2 is the reading for W0 plus 2M and X3 the reading for W0 plus 3M, X4 for W0 plus 4M and S5 for 5M and X6 and X7. Now from using these values of X0 to X7 we can calculate say X3 minus X0. Now X3 minus X0 gives the reading corresponds to 3M minus the reading corresponds to 0 load or weight hanger alone. That gives the shift that produced for a load of 3M. So we are writing here shift in reading for 3M load. Similarly X4 minus X1, that is the reading corresponds to W0 plus 4M minus W0 plus M. That also the shift for 3M. Similarly 5M minus 2M, that is also the shift for 3M. Similarly X6 minus X3 and X7 minus X4 also gives the shift for a mass of 3M. So here we obtain 1, 2, 3, 4 and 5. 5 shift values. So we can add all the 5 and divide by 5. Then we are giving or we are getting the mean shift for a load 3m. So here we obtain the mean shift for a load 3m. Now that value of mean divided by a value 3, we obtain the shift for m. That means shift for a load m. Here in this column we obtain the shift for a load 3m. That value divided by 3 gives the shift for a load m. Then and that shift for load m is marked as S. That is that is the shift for a load m, that is marked as S. So we obtain S here. Yes here. Now using the value of S, and now S is here. A we mentioned, that is the effective length of the optic lever. D is the distance of the scale from the mirror, capital D. We can calculate the value of E, that is SA by 2D. Now we obtain the value of E. All other values are known. The mass that we are suspending in each type, that is 50 gram. P, usually we are taking 10 centimeter. L we mentioned, we initially arranged for a length of 40. Breadth and thickness we measured. Substituting all the values, we can calculate the value of Y, the Young's modulus of the material of the bar. Now to start with the experiment, the experimental bar is already arranged such that L is equal to 40 centimeter. The weight hangers are suspended at a distance of say 10 centimeter each. The optic lever is placed over the experimental bar with the single leg on the experimental bar. Now before starting the experiment, it is better to add and remove some loads one by one, so that the experimental bar is coming to an elastic mode. We can add a number of weights. Now it is loading. We are adding the weights. Now we are not taking the readings. To bring the bar to an elastic mode, we add some weights. We are adding some weights. Now we can remove that weights. To start with, we want initially a load weight hanger alone, and that weight hanger alone is known as W0. Weight hanger alone is known as W0. Now here it is W0 is weight hanger alone. Here also we are removing the load. Then the initial reading or the initial mass suspended is W0 alone. Now we want to focus the scale and telescope arrangement. Now for that, looking through the telescope, the scale is moved such that I can see the image of the scale. The image of the scale can be observed on the mirror there, the mirror of the optic lever. Now I am looking through the telescope. Now I am getting the scale. I can get the scale. I can adjust. The screws can be adjusted so that the scale is clear. The scale is clearly visible. Now the horizontal wire of the telescope is coinciding with the reading 24. Now we can see the reading here. The reading 24 is coinciding with the crosswire. So that is the reading corresponds to the dead load W0. So corresponding to the dead load, we are making the reading. The reading corresponds to dead load is W0, that is 24. That is better. Now we are adding the load on each side. A load of M. Here M is 50 gram. On both the two sides, a load of 50 gram is added. Then what happens that the beam is bended. The center portion is slightly elevated. Then there should be a shift in the scale reading. Now we want to take the new scale reading. Now observing through the telescope. Now the crosswire is coinciding the reading 25.3. So that is the reading corresponds to W0 plus M. So that reading is noted here, that is 25.3, that is noted here. Now it is again loaded, another load, one more load, that is W0 plus 2M. W0 plus 2M is added, 2M. Then again there should be a change in the scale reading. Now I have to take the new scale reading. Now looking through the telescope. Now the new scale reading, that is the reading that is coinciding with the horizontal wire of the telescope is 27.2. So that reading is noted here, 27.2. Then one more load is added. that is W0 plus 3m. W0 plus 3m. Now we have to take the reading. Again, looking through the telescope, we can take the reading. Now the crosswire is reading 28.7. So it is noted 28.7, 28.7. Now one more load is added, that is W0 plus 4m. W0 plus 4m. The reading is again changed. The new reading is taken. Now looking through the telescope. Now the crosswire is coinciding on the reading 30.1. So that reading is noted 30.1. Then again the load is added, that is W0 plus 5m. W0 plus 5m. The load is added. Now the reading corresponds to W0 plus 5em. That is upside here. Crosswire is coinciding 31.6. So 31.6 is the reading corresponds to W0 plus 5em. Then one more load is added, W0 plus 6em. W0 plus 6em. The beam is bending more. So there should be a shift in the scale reading. Now the new scale reading is, the crosswire is coinciding over 33.3. So the new scale reading is 33.3. 33.3. Now we want to unload. For that, now it is W0 plus 6m. 1m each is removed from either side, from either hanger. Now the reading is corresponds to W0 plus 5em. Now take the reading corresponds to W0 plus 5em. That reading is, look the crosswire. The crosswire is reading 32.5. So that reading is noted, that is 32.5. Then one more load is removed. That reading corresponds to W0 plus 4m. W0 plus 4m. Now we want to take the reading corresponds to W0 plus 4m. Now the crosswire is coinciding with 30.1. So 30.1 is noted, 30.1. Now again one more load is removed. That is W0 plus 3m. W0 plus 3m. Now the reading corresponds to W0 plus 3m. That is, crosswire is coinciding with 28.7. So the reading is noted 28.7. Similarly, you remove one more load, then it is W0 plus 2m. Again one is removed, that is W0 plus m. Then one more is removed, then W0. So all that readings are noted here. Now using that readings, we can take the loading and unloading reading. The mean of that two readings gives the values x0, x1, x2, etc. Using that values, we can calculate the shift that produced for a mass of 3m. And then from that, the shift for a mass m can be determined, and that is S. The shift for a mass m is S. Now we can calculate the value of E using the formula E is equal to SA by 2D. S is the shift that we obtained now. A is the length of the optic lever that we calculated by pressing the optic lever on the paper. Then D is the distance that we measured, that is 95 centimeter. We calculate the value of E. Now for the calculation of the Young's modulus, we require the breadth and thickness of the experimental bar. Now for that, the experimental bar using the using a screw gauge, we can take the we can take the thickness, and using the vernier we can take the breadth of the bar. Now with the help of the vernier, the breadth of the bar is determined. Now the MSR reading is 2.8 and the VSR reading is 5. It is repeated at different positions of the bar. There is no change for the MSR. MSR is 2.8 itself, but VSR is now 5. Now another position. Now VSR is changed to a value of 6. So that readings are noted. So the breadth can be calculated. Similarly, to find the thickness of the bar, we are using a screw gauge. So using the screw gauge, the pitch scale reading and the head scale reading we want to determine. Here the pitch scale reading is 5 and the head scale reading is 36 only, 36. So that is also repeated at different points of the scale of the given bar. There is no change for the pitch scale reading. Pitch scale reading is 5 itself, but the head scale reading is changed to a value of 35 now, 35. Again it is repeated at 4 or 5 places of the given bar. Then that readings are tabulated and we can determine the thickness of the bar D. So using all these values we can calculate the Young's modulus of the material of the given bar can be determined. Now coming to a sample set of reading that we obtain here, when we calculated the breadth of the bar, we obtain the MSR reading 2.5 and VSR reading 5, and it is repeated 5 times. The mean value of breadth of the bar is 2.85 into 10 to the power minus 2 we obtain. Then the thickness of the bar, we obtain the least count. The pitch of the screw is 1 millimeter. Number of divisions on the cut scale is 100. So the least count is 0.01. 0 error, 0 correction we noted. Then the pitch scale reading we obtain 5 always. The observed HSR is changing 36, 35, 37, etc. Corrected HSR, the 0 correction is added. So the total is X plus Y into LC, pitch scale reading plus the corrected HSR into least count that we obtained, and the mean value we calculated, that is 5.363 millimeter or 5.363 into 10 to the power of minus 3 meter. So that is the thickness of the bar. Then to find the shift, yes, we mentioned when we suspended a load W0, on loading we are getting reading 24. For W0 plus M the reading is 25.3, W0 for 3M 28.7, for 4M 30.1, for 5M 31.6, and for 6M 33.5, and 7M 34.9. Now unloading, one load is removed, that is W0 plus 6M, then 33.6, W0 plus 5M 32.5, W0 plus 4M 30.1, W0 plus 3M 28.7, W0 plus 2M 27.4, W0 plus M 25.6, W0 24.2. So we are taking the mean of these two, loading and unloading, that is mean 24 and 24.1, 24.1. Similarly, the mean of the all other readings we obtain X0, X1, X2, X3, X4, X5, X6 and X7. Now we are calculating S3 minus X0. Now X3 is 28.75 minus or difference 24.1, that is 4.65. So 4.65 centimeter, all these are in centimeters. So 4.65 centimeter is the shift produced on the scale by a load of 3M, Similarly, X4 minus X1, X4 is 30.1 minus 25.45, that is 4.65 again. X5 minus X2, that is 32.05 minus 27.3, that is 4.75. X6 minus X3, that is 4.8. X7 minus X4, that is 4.8. All these values are the shift that produced for a load of 3M. Now the mean of all these 5 readings, all the 5 are added, divided by 5, that gives the mean shift for 3M, that is 4.76, the mean shift for 3M. Then it is divided by again 3 because 3M is here. Then we obtain the shift for M, that is S. So S we obtain for 4.76 centimeter divided by 3, that is equal to 1.586 centimeter, and that is equal to 1.586 into 10 to the power of minus 2 meter. That is the value of S. Now S is obtained 1.586 into 10 to the power minus 2. Now the effective length of the optic lever A is 3.3 centimeter we obtain, that is 3.3 into 10 to the power minus 2 meter. Then capital D, the distance between the scale and mirror is 95 centimeter, that is 0.95 meter. So elevation E is calculated using the formula SA by 2D, that is equal to 2.754 into 10 to the power minus 4 meter. Now the length, the L of the bar is 40 centimeter, the distance P is 10 centimeter or 0.1 meter, and the mass suspended in each time is 50 gram or 50 into 10 to the power minus 3 kilogram. So we substitute all the values here, then we obtain Y 3 mgp divided by 2 bdq L square by E. We obtain 0.9714 into 10 to the power of 10 Newton meter raised to minus 2. So that is our result, the Young's modulus of the material of the bar.